Okay, let's go. We ready? Okay, I'm just going to make a slight different deviation from what I was going to talk about today. I'm going to talk about, just briefly for the first 10 or 15 minutes, Fisher's test for large matrices. You'll remember that this classic Fisher's exact test was this: male and female, left-handed and right-handed, and you might have 10, 2, 6, and 19 there. And so what this shows is, to a good approximation, all the men are left-handed, and the majority of men are left-handed, and the majority of females are right-handed. And we talked about that and used it, and lots of you are using it in your project. However, there was a whole bunch of people, more than I can remember, who needed a generalization, who needed a generalization of Fisher's exact test, where you had a larger matrix like this. And I'll just take one from education. You had not achieved, merit and excellence, I think it was. And then you had different papers. One was mathematics, and one was English, I think. I can't remember the...
It was all aspects, different papers within maths, but yeah.
Oh, okay. Different education, or it could be male and female as well. And so you had numbers like this. You had numbers like that. And in the same way that we're testing for these rows to be proportional, we can test for these rows here to be proportional with one another with Fisher's exact test. And it works exactly the same. So you're checking for a difference in proportion between the top row and the bottom row, or between the top row of 4 and the bottom row of 4, or alternatively, you're checking for the columns all being the same. And it doesn't look right here, because even if you just look at these two columns here, you can see that there's a very marked difference between these two. These two are about the same here, but these two are very, very different. So I'll just show you how to put that into R. (14, 2, and 6). It reads in columns. 18, 1. 17 and 8. Oops. I'll just take you through this. A becomes matrix, and it reads in columns. So it's 8, 14 for the first column, 2, 6, 18, 1, 17, 8. 2 and 4 mean 2 rows, and 1, 2, 3, 4 columns. There it is. Just do that again. So there's A, and there's Fisher. Let's do that again. There's A, and there's Fisher test of A. So there's your matrix here. You see it hasn't got the nice swanky row names and column names, but we can put those on if we want to. And it's testing the null hypothesis that these numbers are drawn from the same multinomial distribution as those numbers. Okay? With the same p's. It doesn't care what they are, it's just that they're the same. And the p-value is very small, and so you can conclude that there is a difference between the top and the bottom row.
So I could do the same for my fish because I have 4 stages.
Yes, absolutely. This is why I'm mentioning it, because I talked to 3 or 4 or 5 or 6 of you yesterday, and you'd all got the same problem. And so, of course, you can have a bigger one here. You might have some great big matrix with lots of different entries and columns. These might be the different grades and lots of different subjects, or lots of different kinds of fish, or lots of different kinds of whatever it is from your project. So be aware that there's a slight difference in the sense that in the 2 case, in the 2 by 2 case, we've got one-sided and two-sided to worry about, because we were looking at a distribution of odds ratio, and the odds ratio could be larger or smaller, or a two-sided test or a one-sided test. You don't have the issue of one-sided test or two-sided test with the generalization, because there's no way for it to work out an odds ratio, because it's multinomial, not binomial. So the whole thing doesn't work. Sorry.
When you entered it into R, you went being like this.
Yep. I'll show you an alternative to that, just a minute. That's what I said, yeah?
Yeah.
I can do it the other way. See, I'm going in rows now, 18, 17, and then the second row. The question was that I was entering the numbers by columns rather than by rows. If I want to enter it in this order, I can do so, but I need to specify by row equals true to tell it to go alongwards rather than up and down. It's just because computers store it in that order, and that's the way it takes it. I've just reminded myself of something else I wanted to do as well. I just want to make sure everybody seems to be up to speed on this, but I'm gonna cover it anyway. I'm just going to show you, most of you have got your data in some form of spreadsheet. So I'm just going to show you how to get blank workbook. What I'm going to do for you is just to create a very small data set in Excel, and I'll show you how to get that into R. Most of you seem to be happy with this, but I'm just going to make sure I've covered it, especially for the video. So if I say a little data set X and Y, that's going to be 3 and 4. It's going to be 6 and 8.8. That's going to be 2 and 4. 1.1. Oops. 1.1 and 3.1. Nice little data set. I know it's a small one, but there it is. R cannot read, for very good reasons, R cannot read Excel spreadsheets. So the way to solve that, the way to get this data here into your R environment is to do this. What you do is you go File, Save As. I hate Windows 8. Computer. Oh, let's put it on the desktop. We're going to save it as tab delimited text. I'm not a massive expert, but other versions would work, but tab delimited text works quite nicely. So if I just click on that and save there, book 1 already exists. Yeah, replace that. And then it starts whinging about not being able to solve. Well, we'd care. Get rid of that. Don't save. Now, I've saved it on the desktop and it should be there. There it is. If I double click on it, there's my data. To read it, or any variable, call it D for data. Read, oh. D becomes read.table, read the table, file.choose will fire up the file chooser for you to be able to find it using this window here. So where's my desktop? There it is. Book1.txt, double click on it, and it's done it. Oh, a slight problem, it's called V1 and V2. It thinks that the first row is the first data point, and it isn't, that's the heading. That's the file heading.
So you have put heading something?
Yes, yes. So it's the same thing, but I'm telling comma header equals true, and then it knows that the first row is the X and Y. Oh, I need to find it again. There it is. Double click on that. And now you can see it knows that X and Y are the column headings. So that's my X column and that's my Y column. And straight away I can go things like plot Y is a function of X. And I can plot my little data set like that, and it looks great. And I can read it into R and apply my reasoning. Okay. But most people seem to be on top of this anyway, because there were nice examples that people were copying from last year. Sorry, I'm skipping around a little bit here. I'm sorry, I want to go back to my data set here. it's quite possible. What time is it? I'll go through this very quickly. Let me just take this data set here. Oh, I've got it written down here. I'll work out my marginal total. So that's 22. That is 8. This one here is 19. And this one here is 25. So you see 22 people got an NA. 8 people, I'm just totaling the rows, totaling the columns. And here we've got, what's that? That's 35, that's 45. And this one, that's 29, isn't it? Okay. So I can work out my marginal totals, and I guess we can put one down here. That'll be 74. It's possible to work out expected table entries by splitting column totals in proportion to the row sums. Expected on the basis that the null hypothesis is true, which is that the proportions in the multinomial distribution that gave rise to the first 2 rows, or however many rows it is, are the same p's, same p1, p2, p3, p4. I'll make that explicit. Expected And we know that's not the case, because we've already gone through the rigmarole of using Fisher's exact test. I'm just giving you an alternative to Fisher's exact test, which under some circumstances is more powerful. Okay? So I'm just going to make my table here, and you'll see what I'm going to do. This is OBS. This is expected. So the row sums, the 45 and the 29 are the same. So here what I'm going to do is I'm going to take those 22 NAs and I'm going to split them up by this ratio here. So that's going to be 22 times 45 over 74. And this one's going to be 22 times 29 over 74. So you see I'm splitting up that 22 according to 45 and 29 because it's here. And so these two guys will add up to 22 because 45 over 74 and 29 over 74 add up to 1. Yeah? This is going to be the same. That's going to be 8 times 45 over 74. So it can go through all that rigmarole, and I won't go through the whole table, but I'll just talk about it. I'll just do the first couple of rows, really. Twenty-two times what is it? 45 over 74. And the other one was 29, wasn't it? So my expected 13.4, and 8.6, and so on. And so on. Badness equals the sum of O minus E squared over E. Actually, I may as well fill them all in and do it explicitly. I think this is important. The next one's 8, isn't it? See, I'm just getting R to do the work. So the expected ones there are 4.9 and 3.1. The next one is 19. So what I'm doing here, you see this is the split between row 1 and row 2, 45 and 29, because that was the column sum. And I'm just multiplying it in turn by the column sums, 22, 8, and 19 for the third column. So it's 11.6 and 7.4. 7.4 was that? And the final one's what? 25, is that? Here. 15.2, 9.8. So you see the row sums and the column sums are the same for the observed and the expected, and we can work this out. $13.4, I'll go along. 4.9, I can't read my own writing. 11.6, 15.2, 8.6, 3.1, 7.4, 9.8. Two rows. Looks about right, doesn't it? Oh, that's the wrong way around. That's E for expected value, because that's expected on the basis of the null hypothesis. And the observed was the data which I typed in. Expected, observed. We'll just check that the sum of the expected and the sum of the observed is the same, which is good. Sometimes there's a rounding error, which doesn't really matter. So then we can work out a badness, which we've done before, which is the sum of O minus E squared over E, which is 19.6. Chi-squared with how many degrees of freedom? Well, let's have a look at this picture here. Because we know the row sums and the column sums, okay, what that's telling me is that it looks like we've got 8 degrees of freedom here, but we haven't, because what we've got to do is to subtract 1 for each row, and so also subtract 1 for each column as well. Yeah?
So you're subtracting 6?
Something like that. The number of degrees of freedom, it always gets confusing. Degrees of freedom equals R minus 1 times C minus 1, where R and C are the number of rows and number of columns. So it's just 1 in this case. So in that case, it's 3. 3 degrees of freedom. So if the null hypothesis is true, this badness here is chi-squared 3. So I can give you a p-value for that. A lot of learning packed into this. It's p chi-squared because it's the area to the left of this point here, but we want the area to the right, so it's 1 minus. The 3 comes from the 3 degrees of freedom because it's basically because if you didn't know any of these numbers here, I just give you any three numbers and you can fill in the rest of the table from those 3 numbers. All right? Do you want me to take you through that?
Say that again.
If I give you, let's say, 8, 2, and 18, you can work out all the other numbers. You can work out that 17 because you know the row sum. And you can work out that one, that one, that one, and then this one. So you only need 3 degrees of freedom. So there's my p-value. P-value okay. What I've given you, and I want you to pick this up, there's no great magical content here, but what I want you to pick up is that I've given you 2 tests that test the same hypothesis for the same data that give slightly different answers. And sometimes one's appropriate and sometimes the other one's appropriate. I'm spending longer than I wanted to on this. So that gives me a chi-squared on that. And I can also do the same with just chi-squared test of A. Which is not giving me let's just do that again. So this whole rigmarole that I've gone through with observed and expected can be boiled down to chi-squared dot test of A. And you'll see it's given a slightly different p-value, 0.002113 and 204. Very, very similar, but not quite the same. And that's because
If you're not sure if your DF is doing that.
it's not my DF, it's because they've got a continuity correction, which I'm not covering here. So there's some clever stuff behind the scenes here, but it's the same idea.
Still pretty close.
Still pretty close. What I want you to take home is that we've got the same data, 2 tests, same null, start again. Can analyze same data using either Fisher or chi-squared technique. Usually
When we do the
Yep.
the p chi-squared, we have to use that 1 minus, or we can put the
Or lower tail equals true. Yeah, you don't need
lower
to.
tail equals 2 or false.
You want the upper tail, so the lower tail is false. Same thing.
Because I was trying to do this yesterday, and I couldn't remember if I wanted lower tail true or lower tail false.
The way to, if you want to remember, do you remember the lower tail? The way to remember whether it's lower tail or upper tail is to draw a histogram. There's my histogram, and I'll say, well, I've got my badness of 10. Null hypothesis, the p-value is the observation, which is the badness, or worse, which is worse, less, more bad. So it's you always want the upper tail because it's that bad or worse. Yeah, and if you still can't remember, give it some of this. Just have a look at the help page.